Good evening and welcome to the session. It's 6 p.m., but not many have joined, so we'll wait for a few more minutes before we get started. Thank you. Good evening and welcome to week 5 of the live sessions on the fundamentals of additive manufacturing technologies.
Good
I
evening.
am Sourav Goswami, a PhD candidate in the Department of Mechanical Engineering at IIT Bombay. This course is taught by Professor Sajin Kapil, who is a faculty member in the Department of Mechanical Engineering at IIT Guwahati. As per our usual routine, we'll first briefly review the contents that were covered in this week, and then we'll solve a few exemplary problems, which will help us A, refine our concepts, and B, help you solve the assignment problems better, and may even prove useful in the certification exam should you have registered for it. So we'll just start. Yeah. We had been looking at liquid-based additive manufacturing processes. We had already looked at the most predominant and the first developed commercialized process, which was SLA. We'll continue looking at more of its subsystems and also look at some of the other liquid-based AM processes which have commercial use. So as already discussed, the both SLA and SLA-Zephyr used galvanometer as the scanning optics. They both used a sharp pointed laser beam, and the liquid was placed in a vat. The build direction was plus Z in both cases. It's just that the recording system for the case of SLA was deep dipping, where you dip your entire build stage along with the part on it deep into the vat of liquid. You allow an excess amount of liquid to flow over it, and then remove the excess with a doctor's blade or a recoater, and then print your next layer. Whereas in top feeding, you use an array of nozzles to deposit a curtain of liquid on the pre-built surface to a thickness that suits your application. Today we'll be talking about the galvanometer, which you already know consists. Okay, this we have covered some of it. We'll go to the section where we are supposed to start. Yes. So previously we had looked at the galvanometers and we were discussing the advantages and disadvantages of it. So as we know, it has very low inertia and thus which allows for quick movements, and the laser beam can scan with very high speeds up to the order of 10 meter per second as shown here. If we go to higher speeds, as we looked at using numericals in the last session, there is a chance that some of the liquid resin might still remain undercured. Thus, while technologically there is no limit, fundamentally there is a limit on the maximum scanning speed, which actually emerges from the scales at which the liquid resin polymerizes. The galvanometers, being very light and having low inertia, also tend to have longer lives. However, there are a few disadvantages of this technology which led to the development of others. One of it is how the light interacts or how the laser energy interacts with the galvanometer mirrors and tends to get lost in the process, because as we know, no surface is fully reflective. Always some of the energy tends to get absorbed by the material. Some common methods to fix this loss of energy on galvanometers can be, say, using a reflective coating to boost the reflective properties of the mirror. A second method can be to polish the mirror from time to time using mechanical or chemical means as the need might be. However, there are some other issues which are not so easy to fix. They consist of the defocusing of the laser beam on the platform, which we had talked about briefly and we'll illustrate today, and how the spot of the laser beam changes as we scan away from the normal. Now, as we know, the locus of the focal point of the laser beam forms a sphere in 3D space. As long as we are just, say, if we have a galvanometer set up here, as long as our laser beam has to be reflected right under it or along the normal or close or at small angles to the normal, it will fall closely on the surface. We know that there is no one sharp focus. Rather, the beam converges and then diverges. The smallest section is what we called the waist, and we try to keep the waist on the substrate or a suitable distance away based on our requirements. However, when we have to deflect this beam to a farther region, say as shown here, what happens is that the focus tends to shift away from the surface because in 3D space, the locus or the focal points is actually a 3D sphere. So for small angles of deflection, this is pretty okay. For larger angles, we run into problems. Of course, one way to fix this, as Professor Kapil had pointed out in his lectures, is that you increase the height of the build volume. That is, say if this is the height Z H between the galvanometer and your build platform. If you make this height very large, the radius of curvature of the sphere along which the focal points lie will become very large. And in essence, for a very large radius of curvature, you will have an appreciable region which, for all practical purposes, is a straight line and coincides with the plane. And that is one of the reasons why typically 3D printers have such tall build chambers. However, the other way and the more direct way to solve it is by using suitable lenses to focus the spot. One of these is the flat field lens, which ensures that irrespective of the angle of deflection from your incident beam, so the focus will always lie along one plane, which is our target plane. And here, the kinematic relationships work out to be that the distance from this optical axis h equals the focal distance from the lens to the plane f times tan tangent of the angle that the incident ray made with the optical axis. So h equals f tan theta. And when we differentiate it and try to find a relationship between the scanning speed Vh with which I can scan my laser spot on the target surface and the angular velocity with which I can move my galvanometer mirror. Also, the theta at which the incident laser is incident on the galvanometer. We ended up with this relationship where VH is equal to F times omega h by cos square theta. And the thing to note here was that the scanning velocity with which we can scan our laser spot on the target plane is proportional to the angular velocity of the galvanometer and inversely proportional to the angle at which the incident ray was incident on the galvanometer. Thus, to we discussed how it is important to have a uniform scanning speed to have isotropic properties from the printed material. To ensure this, we must carefully actuate both the angular velocity and the angular displacement in order to maintain a uniform velocity of the laser spot on the target surface, which is a difficult task. An example has been worked out here. We'll also look at a few examples during our problem solving period. Now, an improvement over the flat field lenses is something called the F theta lens. And as the name itself suggests, this is related to the distance of the laser spot from the optical axis, h equaling F theta. Here, when we find the relationship between the scanning speed of the laser spot on the target plane with the angular velocity of the galvanometer, we find that it is directly proportional and related by the constant of proportionality, which is nothing but the focal length of the lens from the target surface. This makes our control system much more simpler and easier to handle. The numerical accuracy is far higher, the numerical errors are significantly reduced, and we'll end up with, say, a better print overall. Here, the three types of lenses that we discussed till now are summarized in a slide. So, the typical spherical lenses, in which case, for deflections at small angles to the optical axis, the spot may still be thought to lie in a plane, but for large angles, such as the one shown here, we see that the focus actually moves away significantly from the target plane. The flat field scanning lens, which fulfills our purpose, which ensures that the focal point always lies in the target plane, but where the control and actuation becomes difficult because of the relationship between h and theta and omega, and the f theta scanning lenses, which is the simplest in terms of implementation and the most complicated and sophisticated in terms of design. Now, the this was regarding the defocus of the laser beam on the platform, or the coincidence of the focal point on the target plane. Another issue which arises is of the laser profile or the laser beam spot shape itself. Again, when we are projecting our laser close to the normal axis, the cross section, as shown here, is identical to the original cross section. If the original cross section of the laser beam was circular, when we are projecting it near the optical axis, it still remains circular. However, when we are deflecting it at some large angle away from the optical axis, because of the geometry as shown here, the projection of our originally circular beam on the target surface ends up becoming an ellipse. And how this changes things is that while the incident energy remains same, the energy is now distributed over a larger area. Also, the distribution characteristics themselves may be different, so it might not be equivalent to the case before. As worked out here, this new area, A theta, comes out to be the original area A naught by cos theta. As we know that cos theta is always less than equal to 1. Therefore, A theta will always be greater than equal to A naught. Of course, they'll be equal when theta is equal to 0. That is when the beam is being, there is zero deflection of the beam away from the normal. Thus, again, the requirement of maintaining a constant energy density or a constant surface area energy density is being violated, and thus we can expect anisotropy in properties as we move further away from the normal. A second consideration for this phenomenon is how the energy absorbed by such a beam again is proportional to the cosine of the angle between the striking beam and the normal. So, firstly, the area over which laser energy is distributed is changed. This was our first consideration. Say a circle turns into an ellipse. Second, absorptivity of this energy is also affected. So not only are you now, say, giving a different energy density as input to the system, the system's ability to absorb this energy and say transform it into a visible effect, such as the melting of metal in the case of laser DD type of processes, or in the case of wet photopolymerization, the curing of the resin, both of these things will be affected. And this is as per Beer-Lambert's cosine law. So the energy absorbed when a deflected beam is interacting with the material is cos theta times the energy, maximum energy absorbed, which would have been in the case where the beam is falling or incident normally to the surface. Thus, the ideal solution is where we have some sort of an F theta type of lens, which ensures that the focus of the laser beam does not lie along a sphere in space, but lies along the target plane, combined with a mechanism which allows the rays to be incident normally to the target plane always. And such objectives are achieved by using a telecentric F theta lens. They facilitate the normal incidence of laser beam onto the target plane. However, they have one major disadvantage, which is that the scannable area will be limited by the size of the lenses. So, in the case of galvanometers, even a small lens, I mean, the mirror itself could deflect the beam along a large target area. Even with spherical lenses, that could still be achieved. But with telecentric lenses, given that the beam will always be normal to the surface wherever I am projecting it, we find that the scannable area is indeed limited by the dimensions of the lenses itself. Say it cannot be projected outside this lens. And as we know that making such sophisticated optics is a very costly affair. So we cannot have an arbitrarily large size of telecentric f theta lens in our system to have a larger build volume. This really puts a constraint on our technology. These lenses thus cannot be used to produce normal incidence over large print areas. And this is one of the reasons why we find that often the systems using galvanometers, such as SLA systems, are relatively small in size, say some 250 across 250 square on average. Whereas for wire DAD or arc DAD systems, you can build very large parts in the order of meters. We already discussed this intuitive idea of increasing the height to solve for this. And this is what a modern galvanometer system looks like. So you have these two galvanometer motors, say MY and MX, which actuate rotation about these axes and help to deflect the beam all over the target area. To ensure that the beam profile is maintained as well as that the beam distortion is not there, that is, the focus lies on the target plane. This is combined with this F theta, might as well write it in words, F theta telecentric lens, which ensures that the incidence is always normal to the target plane. The next subsystem which we have to discuss is the recoating subsystem. As we know, for the case of SLA, it consists of deep dipping, and the process is well illustrated here. So once a layer is cured using the UV laser, the entire system with the built part, so this is the built part and the stage, all of it moves in the negative Z direction, which is opposite to the build direction in this case, and a lot of excess material flows over them. This volume of liquid that is flowing over is well in excess of the layer which is required for the layer height which is required for the next step of the build. Thus, even if we are printing just the last layer of the machine, just the last layer of the part, we should have a lot of excess resin in the tank, which is really a wasteful exercise. And it can be thought that this excess resin will never be utilized. Now, once this extra volume of liquid has flown over the pre-built part, the stage rises or the build platform rises again. A doctor's blade or a recoater blade, as the name may be, is used to wipe out some of the excess material, most of the excess material from the top of this pre-built layer, only to leave resin of a thickness which is desired, say TL. There is a scanning system in place which ensures that the requisite height of the resin has been achieved, and then the process continues. Thus, it establishes a new layer of fresh resin. A recoating step would be called successful. Should it be capable of establishing a fresh layer of liquid resin of thickness exactly equal to the desired thickness, because we know that in SLA, SLA is one of the processes with the finest build heights, build layer heights that can be achieved, often in the order of microns. Thus, even small deviations become unacceptable, and it does it within a reasonably short amount of time. Given that because of the motion of the stage and the flow of resin over the pre-built part, there will be perturbations and waves introduced in the resin. Therefore, we must allow some time for it to settle down and reach the steady state. However, this time is not really productive as it is not being utilized for the build, and thus it adds up to the total printing time. Any inaccuracies in the layer thickness will have adverse effects on the final accuracy of the product as expected. And because of all these considerations, the recoating cycle actually is pretty complex in the case of SLA, and it involves multiple stages, those being leveling, deep dipping, elevating, sweeping, obtaining the build position, and then finally weighting, which is Z weight. For the first part, a leveling laser is used to ensure that uh, the surface is at a level or is flat. Typically, the resins will undergo about 5 to 7% volumetric shrinkage upon curing. There's a level compensation system, which can be a contact type using some sort of contact profilometer, or a non-contact type, such as optical or laser-based here, is implemented in SLA. This level compensation system maintains a tolerance in the Z level, so you may have a fixed uh, tolerance level between which your part must comply, and so you can program it. And this leveling system will ensure that for each build layer, that tolerance height, that height is ensured. And should the resin lie within such tolerance limit, the leveling operation is complete and we move on to the next step. If the resin does not lie within this, then excess resin will be allowed to flow over and this process will be repeated. For the deep dipping step, the elevator, which is nothing but the build stage, fully immerses the pre-deposited part to allow the resin to flow over this part. And typical photopolymer resins are viscous, highly viscous, and owing to this viscosity, the resin will take some time before it assumes a level surface over the entire part. And as expected, over sections which might be hollow, there will be a significant depression in the resin surface. And such regions can also lead to the trapping of resin. And in the processes such as SLA, which are uh, recoated by a deep dipping, there is also a chance that the resins in such hollow sections may remain trapped and cannot be taken out later should the build be completed. And there exist some relationships that predict the time it will take for the resin to cover such volumes. So if the time taken is denoted by TD, which is for the depression to be closed on the to be fully covered by the resin, it is found to be proportional to RC, which is the critical circle radius for the cross section. We'll talk about it. Mu, which is the viscosity, and HD square, 1 by HD square, which is actually the height of the depression. A critical circle is one which can be used to fill, or which is the largest circle that can be drawn into the cross section for any layer. So if this green square is my cross section and I try to fit a circle inside it, this red circle is the largest circle that can be drawn. So its corresponding radius, R1, is my critical circle radius. Note that this need not be the smallest or the largest dimension inside. Like here, half the diagonal length would be larger than the circle radius. But this relationship hasn't worked out in terms of this critical circle radius only. For a triangular section such as this, the critical circle again is drawn here. I'm just highlighting it in red. And similarly for any other sections. Formally, it is defined as the maximum distance on any cross section's geometry that the resin must travel to flow off the path. Now, the viscosity is a material property. It is not really in our control. We cannot alter it. It will vary with temperature, but that's about it. The critical circle radius again is a function of the sliced contour. And if our requirement is fixed, we cannot really alter it either. The only possibility of reducing time is by increasing the dipping height. That is, if you have a hollow section, you dip your part very deep into the liquid vat, and we see that the time taken scales inversely with the square of this height, and thus it will fall off very quickly. Professor Kapil also illustrated a calculation on how the timings will change. So I'm not repeating that exercise here. Also, this exercise where we are asked to find the ratio of the deep dipping time required for two cross sections. The only thing to note here is that for the second case, for the first case, the circular cross section and the critical circle coincide. So the critical circle will be coincident with the boundary of this circle, and its radius will simply be d by 2. We have to keep in mind that for this second case, which resembles a donut, the cross section of a donut, the critical circle is not this large circle or even this smaller circle. Rather, it is the largest circle which can lie in the cross section. It is this. And given that the cross section is uniform, the dimension of this circle will be the same everywhere. It can easily be calculated given that we have the diameter of the outer circle and the diameter of the inner circle, and this can be done. We may also attempt it, say. So TD has been found to be proportional to RC. So let's find the critical circle radius for the first case if I'm denoting this as 1 and 2. So for 1, the critical circle radius is nothing but half the diameter of the circle. For the second case is equal to half 3d by 2. Okay, that's the diameter. So half of this minus d by 2. D by 4 minus d by 2, which will equal d by 4. So this is d by 8. So TD1 by TD2 will simply be equal to RC1 by RC2. In this case, they are d by 2 by d by 8 is equal to 8 by 2, which is 4. Thus, for resin to cover the cross section of the first case, it will take 4 times the amount of time that the resin will take to cover the entire cross section in the second case. Minor correction, this is actually excess material. Yes. The third stage is elevating the material once the deep dipping has been completed, and this starts once the depression has closed reasonably. We need not wait for it to close fully, as that might take additional time. But once we are reasonably assured that the depression has been covered, we can begin this next step. Now the platform is elevated until the top layer of the part is above the resin surface. So if we focus on this schematic here, I am again highlighting our built part. And typically one would expect that this build would either be lower than this resin column, so that there is the next layer of resin is on top of it, or in the limiting case may even be coincident with the resin column. However, we find that the part is actually raised above. And why this is done is because we will have a recorder blade coming in from one direction, say from this direction, which will be used to wipe off the excess material. Now, if this blade were to interact with the resin over here, say, that would have led to the formation of some perturbations. And because of the highly viscous nature of the of the polymer, and these perturbations might take a significant amount of time to die down, and the printing process cannot continue further in the case of with the presence of such surface waves or such distribution and perturbations in the liquid vat. It's also mentioned here. Now the recoating blade will travel from one end of the vat to the other and sweeps the excess material. For most part geometries, such a step requires around 5 seconds, and it has been found that the recoating behavior is very sensitive to the presence of trapped volumes. A rule of thumb says that for parts without trapped volume, changing the blade velocity or varying it from 5 millimeter per second to 120 millimeter per second does not have much difference. We can in fact increase it to 120 millimeter per second and have faster build times. However, in the case of trapped volumes, we must keep this velocity very low, because while we are not interacting with the free surface of the resin here, in between, because of the hollow section, the doctor's blade is still interacting with the liquid resin in that region. Again, because of the viscous behavior of the resin, while far away from the blade, we find that the thickness of the new layer of resin is uniform, equal to TL as shown here. In the vicinity of the blade, we find that this layer will vary. Ahead of the blade, there will be a leading edge bulge where the height is very large. On the trailing edge of the blade, while smaller, the thickness of the resin is still far in excess of the required layer thickness. And thus we should endeavor to find a relationship between this trailing edge thickness of the resin and the steady state thickness which is needed for us. And such a computation has already been performed, and it has been found that to ensure steady state layer thickness TL, we must have a lagging edge thickness of the resin twice of that. So Lg should equal twice the desired thickness. This is of course based on the assumption of a velocity profile that varies, say, in a triangular fashion. If some other variation of the resin velocity is known or is observed, of course this relationship will change suitably. The next step is actually obtaining the build position. So the elevator is lowered again and the part is in the right position for scanning the next layer. The resin surface after this stage will still be disturbed because you moved the elevator again, even by a small distance. In particular, owing to the finite surface tension effects, there is usually a visible crease at the solid to liquid interface around the perimeter of the part. And such creases will fade away exponentially over time. So if we give it some weight, it is reasonable to expect that the creases fade away. This period is called the Z wait, and the waiting period is introduced for the resin surface to blend and reach the configuration as shown in this figure. Now, the wait period is usually determined through a compromise between surface non-uniformity and build time. If build time is not a constraint and your machine availability is not a constraint, you can wait for significant amounts of time to allow the resin to come to a complete standstill before proceeding with curing the next layer. However, that is not really feasible most of the times. So we'll wait for a reasonable amount of time, but not wait for it to die down completely and then proceed with printing or depositing the next layer. Now one needs to choose a longer Z wait time when a large TL is chosen. So the Z wait is directly proportional to the layer thickness. If we are working with very thick layers, we must wait a longer time. However, with current technology, it is possible to complete computation and adjustment of resin layer per layer within 1 second itself, and thus the waiting times have been brought down substantially. However, owing to the small layer thicknesses, it is also mentioned that any practical parts which would be built with such a process would be consisting of thousands of layers. So over these layers, even those single or 2 seconds will add up. Now, in contrast to the traditional SLA system, which used deep dipping, we have a top fitting mechanism in the modified or upgraded Zephyr version. And the Zephyr system uses a vacuum blade, which will pick up resin from one side of the vat and apply a thin curtain of resin while sweeping across. This will speed up the build process time because now you no longer need to deep dip, then come up again with excess material, wait for it to stabilize, take away the excess material with the doctor's blade, go down, wait to stabilize again, have the Z wait period, and then start printing the next layer. You just deposit a thin curtain of layer of necessary thickness. Now the control over that thickness is a whole together different question. It is not always possible to achieve the exact level of accuracy which would have been possible with the traditional SLA, but this is the trade-off between accuracy and build time. It has also been seen to make dealing with geometries which might have trapped volume a lot more tractable. Now, the final subsystem involves the Z-axis of the machine, which may either be actuated using some lead screw or ball screws. It may be actuated using a rack and pinion mechanism, or for the simplest case, may simply use parallel kinematics from something called a scissor lift, which can have a very small footprint in the build plane and can achieve substantial build heights. Now that does it for SLA and SLA-ZFL. Now we look at a few other uh, liquid AM processes or AM processes that utilize a liquid material as the feedstock. Some of them are named here. One is per factory, the other is object polyjet. Both are commercial systems which have been put to commercial use or applications. Now for per factory, the scanning system consists of a digital light processing unit or a digital mirror device unit. The shape of the UV light instead of a pointed laser beam is in the form of a floodlight. The liquid still is in the shape of a vat. The build direction is along -z, and we utilize bottom feeding. And per factory, in fact, is the system with the best cost to performance ratio, providing better accuracy and resolution than SLA at far lower costs. It is driven by the digital light processing technology. Let's write it here, DLP. And a schematic of such a system is shown here. So here you have the optical system at the bottom of the build plate, sorry, below the build plate, and it actually consists of a large array of mirrors, which are all fixed or which are held together along their diagonals and can be actuated using electromagnetic coils. Now, the container or the vat is in fact transparent to this wavelength of the UV laser used, of the UV light used. A UV lamp is used to flood the digital mirror device. Depending on the active pixels or the areas in your current slice which you want to be cured and which you want to remain uncured, the mirrors are actuated and the entire area is exposed at once. This greatly reduces the time which say a system like SLA would have required because it scans the entire area of interest point by point by scanning a laser. In this case, we are exposing the entire area in a single go. Again, because of how the energy is placed here from below the liquid vat, the build direction is along the negative z direction. A side view is also shown here. And for perfectory, a few major steps are listed here. The first, of course, is exposure, where the region of interest is exposed to the incident UV light. Peeling, or because this the light UV light is coming from the bottom and the resin is in contact with the glass window while it is getting cured, there is a good chance that after curing it may remain stuck to this transparent glass window. Over time, such remnants of solidified resin may continue to aggregate around the window and affect its transparency to the incident light. Thus, it has to be cleared. The second stage is peeling, which here is shown via some shaking or vibratory action. However, this might not be the most efficient way to do it. Then we wait while gravity does its job, and by the virtue of gravity itself, the resin from the surrounding regions flows into this cavity and for the building the next layer. And the final step is leveling, where we bring the printed part down to a height such that only the necessary uh, height of the column of resin remains. All these steps were illustrated in the lecture, and the system has certain key features. Just by inverting the build platform, the part quality and speed are improved. The cycle times are reduced because, as we discussed, the entire region of interest is being exposed and illuminated in one go rather than, say, scanning it point by point. The need for support structures is also minimized. because for certain geometries, such as I would show here, say if you want to print a hollow sphere, and if I were to build it along the positive z direction, in one case, I would be requiring support structures at the bottom, which allow me to separate it from the build plate later on. Also because this part has overhangs. Here, because of the explicit overhangs, and also inside. And since this hollow sphere is closed, I will not even have any recourse or any method to remove these support structures later on. Now consider building the same geometry upside down. Support structures will be required here, but that's about it. No more support structures are needed. And also, because it is inverted, in every step, the liquid resin, which might have been in this region, will flow out under the action of gravity. And there is very tiny chance of entrapment of this excess resin inside the hollow part. Again, we are not using a laser, rather we are using a floodlight which illuminates this entire region in a single go. And the mask projection with DLP based optical semiconductor technology is used. Such mirrors also have a very long lifetime of up to 22,000 hours. The other build, the other advantage, as we'll see here, and you might also have a similar question in your assignments, is when we try to calculate the build time using Envision's Perfectory and any other system such as an SLA, and we try to see what will be the ratio of the build times. In here, one case, on the case on the left, you only have one cylinder, so that you are trying to print. In the other case, you have an array of 20 cylinders, 25 cylinders. Now, had it been a system such as SLA where you use a sharp laser point to scan the entire region of interest, the build time would have scaled with the volume of the print. So, with the area to be covered in each slice, as well as with the total number of slices itself. So, area times height, the volume. Whereas in the case of perfect tree, given that we can expose the entire region of interest or the entire build surface in one go. I am not exposing certain regions only because it is not desirable and I don't want any material to be printed in that region. But should the need arise, I can still expose the entire region in one go. So whether it is just, say for one layer, I want to expose just this one cylinder on the left, or whether I want to expose all of these 25 cylinders, such as on the right, it is the same step. I do not require any additional effort or any additional time or any additional energy for this. So in the case of perfect tree, the build time scales with the height of the part. In the case of say SLA, the build time would have scaled with the volume of the build. Again, the second step would be recoating, which can use either a peeling or sliding type of mechanism or the shaking mechanism which we saw. Let us look at the optics, which in this case was a digital mirror device or the digital light processing unit, also sometimes called a digital micromirror device because the mirrors are at the micron scale. Here we have a schematic. So a digital micromirror device is a binary light modulator that consists of a rectangular array of square micromirrors that can be tilted around their diagonals into one or two stable configurations. When the device is not powered, the micromirrors lie flat, meaning that normal to the surface of each micromirror is aligned with the optical axis, or there might be a very small angle, as we can see here. When the DMD is powered on, the micromirrors can be individually actuated and rotated into either of their two fixed operating positions. These positions being the mirror tilted around 12 degrees from the normal to the surface of the device, which is called the on state, or the other state, which is the off state. So typically, I would have the mirror lying nearly flat. This is the off state. Typically, I'll have the micromirror lying almost normally to the incident light so that the incident light bounces back in the same direction and does not reach the build platform. However, when I actuate it using some electromagnetic coils into the on state, the mirror will tilt around its diagonal at a suitable angle so that the incident light is now reflected onto the build platform and cures the resin. And here is a schematic of the mirrors, and there are certain terminologies to be covered here. They are also described in later slides. Professor Kapil also showed an ingenious, say, macro scale reconstruction of the DLP technology, which I found highly entertaining and educational. Now, the masses of each of these micrometers is again very low and does not create any noise. As we already said, the DMD has quite a significant lifetime of up to 22,000 hours. In this case, the micrometer pitch is this center to center distance between the centers of adjacent micrometers. For a square array, it will be equal along all directions. However, for rectangular arrays, it might be different, or will be axially. It'll change axially. The micrometer size is the linear dimension of one mirror, and via is a small non-reflecting part in the center of each micromirror through which this mirror is mounted onto the underlying hinge structure. Similar to how we discretize any 2D surface into pixels, and typically these pixels have an aspect ratio of 1, that is, they are square, and the length is equal to the width. Similarly, if we are to discretize a 3D volume, which is needed for our 3D printing process, we extend this concept to 3 dimensions and call it a voxel. And here the resolution of our DMD process has been calculated. So if this is a digital mirror chip with a total area of A cross B, and it has been discretized into these number of mirrors, each mirror assumed square with a side of small a. Now we know that the total number of pixels on this DMD chip will simply be A cross B. If the total build area to be scanned is XY, then per pixel, the area which must be scanned or which it should cover corresponds to the total area to be scanned by the number of pixels, which is nothing but xy by AB. Also, since typically we will only have square pixels, we can also divide this area uh, across those two dimensions. So for a square region of size AP, you will have AP square equals this area xy by AB. Thus, we can find the area of the dimension of each pixel. An example calculation has also been shown here. We'll also discuss something in our problem solving duration. Now comes the recoating cycle, which consists of peeling the previously built layer away from the transparent window, waiting for the resin to occupy this vacant space, and then leveling or the motion of the stage down again, just to ensure that only the requisite amount of resin now remains ready for the next printing layer. Now, as we were discussing, it might happen that in certain cases or with time, with increasing number of layers, the peeling process is not very effective, and there is always some remnant in each step. Over time, this remnant may build up over the glass windows, and that can affect the transparency of the window to the incident UV light. One way to deal with it is to actually have a small cushion of oxygen. So in this case, you have this window is made of silicone, or maybe it was silicone only. You have a small window of silicone through which you allow oxygen to permeate, and this oxygen forms a small cushion and does not really allow the part that is being printed to come in contact with the window. It maintains a very fine gap, and this can prevent some of the issues that we were discussing. However, it would require a constant pumping of oxygen into this region, and oxygen, as you know, is highly inflammable. So this is not really, say, a commercially viable idea. A second way is to actually use a recoating window which is transparent, so that when you try to peel off the part from the window, it comes off easier. A second way to achieve this is that rather than pulling away your, say, if this is the build part, this is the build plate, and this is the part which has been printed till now. This is the transparent window. This is my build platform. So rather than always pulling vertically, which will incur a large amount of force and may also deform the build part or introduce instabilities into the liquid resin, for which we must wait for them to die down. We can also alternatively slide along this window to ensure that the previously built layers come off from the window and the liquid resin can flow in. This is accomplished here by a sliding action where you have, say, if I draw the top view, so say in one side, the it is not really flat, so in one side you have a large gap between the pre-built part and the base of the jar, and in the other case you have the optimum gap, and initially your part is, say, printed here, then either the part or the this jar itself slides along. There is relative motion between the two, and your part comes to this other direction. Now it will take the excess amount of resin will flow under the part, and then there will be relative motion again, and either the jar moves or your part moves and comes back to the region with the optimum gap. Now you have just the amount of resin which is needed for the next printing layer, and then you can continue. So such sliding based recoating mechanisms have also been implemented. The other technology is object polyjet, which has both the flying liquid and the flying optics in its scanning system, which uses a floodlight, has a jet of liquid builds along the Z direction and utilizes top feeding. In principle, it is very similar to stereolithography, and you have a light of appropriate wavelength which falls on liquid photopolymer, and the absorbed energy results in polymerization. Principle similar to inkjet printing is used. We just extend it to 3 dimensions. But where the difference lies is that here you have support structures made out of a different material compared to the build material. Whereas in SLA, it was not really possible as the vat was filled with resin of only one material. Now, based on the printing strategy or the density or the amount of, say, input power, we could selectively make the support structures weaker than the built material itself, or we could make them of the same strength, then take out the system, break away the support structures, and then further cure the built part into in a UV chamber. In this case, we build the support structures outright with a different material, which will be weaker, or which will have some selective solubility properties, which with a suitable reagent. Say in this case, the supporting materials can simply be washed off with water. They are water soluble. Also, it uses raster-based printing technology. Here we have multiple jets, say up to 8 pairs of jets, which drop a curtain of liquid on the top surface. Also fitted to the head are the UV light sources, which cure the deposited resin layer almost instantaneously. Thus, this UV light must be of a higher power than, say, one used in the vat photopolymerization. Explicit support structures are needed as this is a build process along the positive Z direction. For object polyjet, water-soluble gel is used as the support, which is not photosensitive. It will not get cured by the UV light. And the support is simply blown off with a jet of water. Now, because of the use of the multiple heads for jetting, you can have synchronous jetting, and you can jet simultaneously from you can jet identical amounts of resin. You can have layer thicknesses of up to 16 microns. And as we discussed, since the UV light is also fitted onto the dispensing head itself, with the motion of the dispensing head, the UV light also moves and the curing is almost instantaneous. There's little to no post-processing needed apart from the removal of the support structures. Since the heads are discrete and multiple, they are easy to replace, and standard procedures and standard parts exist should such a head be malfunctioning, and it is highly suitable for office environments. The advantages of object polyjet are that it has quality parts. So, okay, something wrong. Yes. You can make quality parts which are highly accurate, detailed, have a very good surface finish with any complex geometry. It is a fast process because we only use rastering along the X direction. Along the other direction, it is just indexing, that is to cover a surface area and say this is your head. It will deposit along this entire region in a single go. To cover the next region, it will simply index to the next position. That is, it will move by a finite amount and then deposit the resin wherever needed again. Also cure it. For the third pass, it will simply again index to a third position. If we consider this the y-axis, so the y-axis is simply an indexing operation. The printed parts have good material properties, that is, they have good flexibility, they have good impact strength, and can also be made transparent, or transparent products can also be produced using this process. It is very easy to operate and reliable. It is good for office environment, and the support structure are easily removable just by dissolving in water. No post curing is needed, as was needed in SLA using a UV chamber. Should a pair of nozzles get clogged, they can be individually removed and replaced. Any limitations are same as those for the SLA process. Finally, we will look at some of the other liquid-based AM processes which might not have gained much commercial viability or which may not be suitable to produce a wide variety of parts. Among them are Autostrad's EDART, a technology called solid ground curing, microstereolithography, and robotic SLA, and some other processes such as rapid freezing. Now, Autostrad's EDART is based on flying optics using a laser beam and a liquid vat to build parts along the negative Z direction using bottom feeding. Of course, since the build is along negative Z, it should have bottom feeding. It's a Japanese technology, and the setup is illustrated here. So in this case, rather than moving the vat of liquid, we are moving the optics itself. The optics, in this case the laser source, is mounted on this X and Y stage and can move to cover or illuminate the entire region of interest. Now, the advantage in this case would be that because the vat of liquid is not moving, there will be little to no instabilities or surface perturbations, which might be induced due to inertia effects from the motion of the vat. However, on the flip side, as we are well aware, the laser optics are actually the most fragile part of any uh, say laser processing system. And in this case, the laser optics itself is being moved or traversed along the XY directions. Thus, this process is very slow as you cannot really move the laser and the optics at high speeds to cover the region of interest. We must move at very low speeds. The rest of it is similar to any other bottom-fed process which builds parts along the negative Y direction. So the setup of the laser is found under the resin tank. Laser beam is directed into the resin, and the system uses an acrylic resin to produce models. Some of its advantages are the same as would be associated with any technology using a top-down build strategy. And since the laser is moving along this X and Y directions, and the incident ray is always perpendicular to the glass window, this beam correction or beam correcting lenses are not needed. However, because of the limitation of or the fragility of the laser optics, we cannot really move at great speeds to cover the area of interest. We must traverse only at slow speeds. Thus, this process is significantly slower compared to others such as perfectray or SLA. The next technology, solid ground curing, uses a mask as a scanning system with a floodlight and a liquid vat to build parts along the Z direction using top feeding. And it is developed by Cubital. It is very similar to SLA, where you have a light of appropriate wavelength falling on the liquid photopolymer and leading to polymerization and curing. However, instead of a laser beam which is used in SLA, here you have a flood of UV light, and we use masks, optical masks, to filter out the areas which we want to get cured or to remain uncured. This mask is the region of the region to be a negative of the region to be polymerized, and the regions where the light falls become solid. From the remaining regions, the liquid can be drained out and replaced by liquid wax. Again, since it uses floodlight technology, the process is fast. Build time is proportional to the height of the object and not the volume. The power of the laser and the exposure time will decide the layer thickness, and explicit support structure are required. However, instead of say finding the intersection of the slicing planes with the contours and looking at the uh, normals, components of the normals of each facet and comparing them to find whether support structure will be needed or not. If needed, they must be generated during the pre-processing cycle itself. In this case, such explicit calculations and explicit generation of support is not needed. Simply the regions where supports are to be made is filled by pouring wax, and thus this eliminates the need for any pre-processing for support calculations. The major steps are illustrated here. So you have the creation of the photomask, the recoating of the resin using something like a vacuum blade or a recoater. On top of this, the photomask is placed and the UV lamp is turned on. Again, as we had discussed, we must be careful how the shape of the mask is distorted with respect to the shape that actually falls on the part. So if this distance is very large, we can expect that the shape that is projected onto the resin may vary significantly in dimensions with respect to the original intended size of the mask. Now, after this short curing or partial curing process, the uncured or the excess liquid is removed using something like a vacuum blade, and this entire region is recoated with liquid wax. This liquid wax may also be frozen using a cold plate rather than waiting for a long time for it to cool down and freeze by itself. And once the wax is frozen using this cold plate, a face milling operation is performed to ensure Z accuracy. Once Z accuracy is achieved, you have the final curing with say a high power UV lamp. So this was only partial. And then with the next layer, this process repeats itself. Some advantages and limitations. So the entire layer is exposed in one go, hence it is very quick. The high speed allows production like fabrication of many parts or large parts. Minimum to no post cure required. The milling step that we saw here after the freezing of the liquid wax ensures flatness and accuracy for subsequent layer and Z accuracy. Supports are obtained by filling the wax and sucking the liquid polymer. No extra support calculations at the pre-processing stage are needed. Some of the limitations are that the process has two cycles and multiple subsystems, making it very complex. Hence, it is less reliable at all of these individual subsystems may be prone to, say, malfunctions or being stood up, and that will interrupt the entire production cycle. Also, it requires full-time operator attention, as for example, if you let the liquid wax remain in the pipelines for long, it might simply freeze there, clogging the pipeline, which will stall production. The building time depends only on the height of the part and not its volume. So even if you have a very slender part, which does not have a large volume, but is very long, and there are constraints which force you to put it or align it along with the build direction only. Even for this small part, you will require a large build time. The dewaxing process is highly time consuming and a lot of wax is wasted, which cannot be recovered. Next, we have microstereolithography, where all the X, Y, and Z movements are where the XY movement is with the vat of liquid and the Z movement is with the stage. And it's a very slow process with an accuracy of up to 10 micrometer, which has also been shown to be able to print ceramics using vat photopolymerization. Robotic SLA, a process similar to something we had discussed and also seen a video of in one of the previous sessions, where rather than having a fixed build direction, your build direction is variable, which allows you to build even, say, typically overhanging parts without the need for any explicit support structures and can be used to print complex geometries. However, this technology is yet to be commercialized and has only been demonstrated in scientific literature. There is also something called a two laser beam system, which Professor Kapil discussed. I am not repeating it again. Uh, while it is very novel, it has more issues than applications at this time, and thus has not seen the light of day for commercial applications. Another is called volumetric stereolithography, which has been developed at the Lawrence Livermore National Laboratory and uses the concept of holographic projections to cure a 3D part. And finally, there is something called rapid freezing, which is basically freezing of water to make parts such as molds or prototypes and other stuff. Here again, you can use different materials for building the main build material or the part material and the support material. So typically you use pure water for the build and saline water, which is a eutectic sugar solution for the support material. The advantage is that the support material will simply dissolve away or will simply melt away at -4 degrees, whereas your part, which is built of pure water, will melt only at 0 degrees Celsius. Thus, by varying the temperature, you can simply melt away the support. It may also be possible to sublime the support structure away by suitable combination of temperature and pressure. We are done recapitulating. Let us take a short break here and then we'll continue with solving some exercises for this week. Welcome back, and let us continue with our session. So now we'll now look at a few illustrative problems which will help revise and refine our concepts from the lectures as well as help you in answering the assignment questions. So the first one, a single axis galvanometer with a range of plus minus 20 degrees is used in an SLA process. The laser beam deflected from galvanometer passes through a flat field lens to keep the focal point at a distance of 300 mm on top of the resin surface. What will be the difference between the maximum and the minimum angular velocities of the galvanometer in order to keep the constant velocity of the laser beam spot at 10 meter per second? This uses a flat field lens which would guide us to the relevant formula. In this case, the formula was omega h is equal to Vh cos square theta by f, which actually comes from Vh is equal to f omega h by cos square theta. The formula has been derived by Professor Kapil in the lectures, so I'm just referring to the ready formula. And here the given parameters. So here the given parameters are that theta must vary between minus 20 degree and 20 degrees. The focal distance is given to be 300 mm, which in SI units is 0.3 meters, and the constant velocity of the laser which is to be maintained is 10 meter per second. So omega h is equal to Vh cos square theta by f is equal to 10 meter per second into cos square theta by f is 0.3, so 33.33 cos square theta. Now for theta equals 0 degrees, omega shall equal 33.33 cos square of 0, which is 33.33 radian per second, which in fact is the maximum velocity because the velocity will vary with cos square of theta. We know that maximum value of this is 1, minimum is 0. So this is the maximum omega that can be achieved. For theta equals 20 degrees, omega shall equal again 33.33 cos square of 20 degrees. This comes out to be 33.33 into 0.8830, which is 29.43 radians per second, which is in fact the minimum angular velocity that can be achieved for this case. As it varies with the cos square of theta, it does not matter whether we use plus 20 degrees or minus 20 degrees. Both calculations using either angle will give me the same value of the velocity. And, I mean, to summarize, we can write that to maintain VH equals 10 meter per second, the angular velocities must lie between 29.43 radian per second and 33.33 radians per second. This is the required answer for this question. The second one, again on galvanometer. A single axis galvanometer with a range of plus minus 25 degrees is used in an SLA process. The deflected beam passes through an F theta lens to keep the focal point to distance on top of the resin surface. Area of the circular laser beam spot is only 2 mm square. What will be the laser beam spot area if it is deflected by a large angle of 20 degrees? Again, we discussed at length how when the light or the laser beam is incident normal to the surface or close to the optical axis, the beam profile remains circular. However, when it is deflected by large angles, because of the geometric constraints, the beam profile on the surface is rather an ellipse, which leads to a redistribution of energy across the surface of the resin. We are asked to find this modified beam spot area. Again, the formula for this was discussed by Professor Kapil in class. So if the original spot area is A naught, the new spot area after deflection of the beam by an angle of theta, A theta is equal to A naught by cos theta. We already have A naught, it is equal to 2 mm per second, and theta in this case is 20 degrees. Therefore, the new area A theta will come out to be A naught by cos theta, which is 2 by cos of 20 degrees. So just give me a minute, I'll work it out. This comes out to be 2 by 0.9397 millimeter square, which is 2.1284. So as expected, it is larger than the original nominal beam spot size. Thus, even if the same amount of energy, if we keep the power constant, because of the change in the cross-section area or the beam, the incident energy or the energy density per unit area is changing. This may give rise to an anisotropy in the properties of the printed material. The third question asks us, what is the advantage of using parallel kinematics in the z-axis subsystem of SLA systems? Does it come at a lower cost? Well, during our lectures, we did not really discuss this aspect of cost, but there is no specific aspect which makes us or forces us to or allows us to have a reasonable guess that the costs may be lower or higher than the other system, such as rack and pinion or others. So this is questionable. It may or may not be true. However, we cannot definitely say it is true. Is it faster than lead screw or ball screws? Again, during the course of the lectures, there was no particular reason for us to assume that the pedal kinematics will be faster than lead screws. In fact, it may indeed be slower than the lead screws or ball screws. So this is wrong. Can it obtain a relatively larger build volume? Yes, as we saw that with the use of parallel kinematics, such as a scissor lift, we can really have tall build volumes uh, with very low footprint in the build plane. This option is correct because they can be used serially to have large Z build heights. And as we saw, such mechanisms always have a very small footprint in the XY plane, which in this case coincides with the build plane. So options A and B are correct for this case. Question 4 is asking us, in the context of 3D systems SLA process, what should be the gap between the doctor blade or the sweeping blade and the pre-built layer in order to obtain 10 micrometer thickness of the layer? So just a quick schematic. This is my vat. This is my build stage. This is my part. We saw how the part, in fact, is protruding some distance out of the liquid vat. On top of it is the excess resin. We only want a definite amount of resin here. Let that be given by TL. We also have a doctor's blade which will sweep away the excess material. However, it is at a larger distance of, let's call that LG. And we saw that how these quantities are related is that TL was found to be LG by 2 for a triangular distribution of fluid velocity or resin velocity. It's important to keep this in mind because for any other distribution of the velocity, the relationship will change. However, since nothing is explicitly mentioned, we may assume that the distribution of fluid velocity is still triangular in this case. And here TL will be equal to Lg by 2. Here the layer thickness TL is given to us, which is 10 micron. Whereas to find the gap between the doctor blade and the pre-built layer, which is Lg, it will simply be equal to 2L, which is 2 times 10 micrometer, which is 20 micrometer. So option C is the correct answer here. Question 5 is asking us that build times are proportional to some quantity or some parameter in SLA and some parameter in per factory. What are those parameters? And we see that all the options consist of height, volume, or a combination of the two. Now, as we discussed in SLA, you use a laser as the energy source, and thus you scan point by point over the entire region of interest, and then you, in one slice, of course, and then there are multiple number of slices. Whereas in the case of per factory, we saw how it uses a floodlight. We illuminate or expose the entire region of interest in a slice, in one go, and number of slices, of course, play a part. Now, because of the nature in which they are exposing the slices in SLA, for each slice, the area matters and the total number of slices matter as well. So SLA is proportional to in build times are of SLA are proportional to the volume, whereas in per factory we saw that in each slice it does not really matter as to what is the area that is to be scanned or exposed because I can expose my entire build plate in a single go. I preferentially do not expose some regions because I do not want to cure them. However, the number of layers will impose constraints. And so, in this case, or in the case of per factory, the build time is only proportional to the height of the build. So, corresponding to this, we see that option B is correct. Question 6, again, dealing with per factory. So, in per factory, a digital micromirror device of resolution 2048 into 1024 is used. If the working area or build area is 300 into 150 millimeters square, find out the resolution of the machine at maximum work area setting. So detailed calculations and derivations were covered in Professor Kapil's slides. I'll directly start from the formula. So the total number of pixels given to us is 2048 times 1024, which comes out to be 2097152, and the working area given to us is 300 into 150 millimeter square. So the area available per pixel it was denoted in the slides by capital AP. I'll use the same notation equals the working area by the number of pixels, which is equal to 300 into 150 by 2097152, which comes out to be, just give me a minute, I'll work this out. This comes out to be 0.0214 millimeter square. Now, assuming square pixels of side small ap, you have ap square equals this area capital AP, which is 0.0214 millimeter square. Therefore, the length or the dimension of each such small mirror is equal to the under root of 0.0214 mm, which comes out to be 0.1465 mm. Is a required answer for this case. The next question, question 7. Which of the following statements are true with regards to energy sources in liquid AM processes? So we'll have to examine each statement and check whether they are true or false. The first statement, lasers are coherent, monochromatic, and cost effective. As we saw, lasers are indeed coherent. That is, there is no phase lag or phase lead uh, between the electromagnetic waves that are constituting a laser beam. Lasers are monochromatic, so they will typically have only a single wavelength, but they are not cost effective. In fact, they are highly cost intensive. So this statement is wrong. Flood lighting is coherent, monochromatic, and cost effective. Flood lighting is not coherent, whereas it can be monochromatic and it is cost effective. So this statement is also wrong. Lasers are monochromatic, whereas floodlight is coherent. As we already saw, floodlight is not coherent, so this is wrong. It only leaves option D. Let us see if it is correct. Floodlighting is monochromatic and cost effective. This is correct. So option D is the correct pick here. We have to be careful as mostly the assignment questions are of multiple correct type. So we must examine each statement for its own merit. What physical principle is utilized for sliding based recording system in envisioned text per factory? Is it that sliding requires less force due to shearing of liquid resin layers? Sliding ensures uniform recoating of resin for the next cycle. Sliding is a simpler mechanism than using a recoater blade, or inertia of sliding ensures liquid resin fills up the voids and pores of the previous layer. I see multiple statements which are correct, but we are asked to find the or state the physical principle. Professor Kapil also demonstrated how pulling the material away or peeling the pre-built part away normally from the resin surface induced around 3 to 4 times more force than trying to shear it away. Thus, we must look at what is the physical principle or mechanism that makes shearing easier than normal pulling. And because we are dealing with liquids, we know that with fluids, we know that by definition, fluids cannot sustain even infinitesimally small amounts of shear stresses. They simply deform under the action of even infinitesimal shear. This is the physical principle which is exploited in this case. That is, the shearing of the liquid resin layers is exploited during sliding based recoating systems. The other statements may be true, but they do not really reflect the physical principle of the process. It is the shearing. Question 9 is rather straightforward. Which material is used for generating support structures in object polyjet? Is it same as the build material? Is it a water soluble gel? Are no support structures needed, or is it wax? Now, if you remember object polyjet, we used a different material for support structures. It was not wax. That was the case for solid ground curing. Explicit support structures were needed, and it is indeed the water soluble gel, which could be used as a support structure. It also had a specific name. Yeah, in this case, it was full cure S, which was used as the support material, and it is water soluble. Question 10 is asking us which is the correct statement in the context of UV power of object polyjet versus envisions per factory. So let us try to think about it. In object polyjet, as we just saw, a curtain of the liquid resin is dispersed through the nozzles and it is almost instantaneously cured by the UV lights that are mounted on the dispensing head itself. Since this process is very quick, almost instantaneous, the laser power, the UV light must be of sufficiently high power. Whereas in per factory, this need not necessarily be the case. In fact, per factory uses the digital mirror devices, but there is no dependency, there is no constraint of time, and so the powers need not be as high. So the UV power is higher in object polyjet than envision per factory because of flying optics. This statement is correct. It is lower than envision's per factory because of multiple jetting nozzles. No, jetting nozzles are not really related to the power of the process. It is lower than envision's per factory because of lower layer thickness. This may have been viable, but we know that it is not true. It is same as envision's per factory. Not always. It has to be higher because of the requirement we just discussed. The curing must take place almost instantaneously, which is only possible with a high power UV laser. Whereas for envision's per factory, the UV laser may be of a similar wattage to SLA, so say of the order of 40 or 50 milliwatt only. So option A is correct for this question. Question 11. What is the purpose of face milling operation in solid ground curing? So if we remember, in solid ground curing, we would take away all the uncured resin and fill it with liquid wax. Then we would use a cold plate to freeze that wax, and then a face milling operation was performed. But what was the purpose of that operation? Was it to ensure good surface finish? So our wax is really a waste material. We are not building the part out of that wax. So it was not used for, it will not affect the final surface finish because all of it is anyway going to be removed. So option A is incorrect. To remove the wax before deposition of next resin layer, we do remove excess wax using this solid ground curing, but the rest of the wax is still there. In fact, it is needed as support structure to support the part that is cured. So option B is also incorrect. To maintain Z direction accuracy, this is correct. We perform the face milling operation to ensure the accuracy of build height in the Z direction and to correct it suitably if needed. Option D is simply nota. So option C is the correct answer in this case. Question 12 says, which of the following processes does not require the explicit calculation of support structures? Is it solid ground curing? So as we were just discussing in solid ground curing, we use molten wax to fill the uncured regions after taking the uncured resin away, liquid resin away. And we do not build explicit support structures from the build material or a different material. It is the liquid wax itself which acts as the supporting structures. So option A is correct. Envision text perfectory. No, in perfectory, the explicit support structures may still be needed and they will have to be factored in during the pre-processing stage itself. Robotic SLA. So as we saw in the case of robotic SLA, we may actuate our robotic arm in such a fashion that support structures themselves may not be required. Since support structure itself is not required, we need not perform any explicit calculations for where they might be required or not. So robotic SLA also fits the bill. Option D says both A and C. So in this case, option D is the most suitable and is the correct option. So that is all I had for this week. Thank you very much for sticking till now. There is a question from Prakash Balan. He is asking for repetition of previous question. Prakash, could you please mention the question number in the chat and we'll go over it again. Fourth question. Okay. So this had to do with the gap between the doctor blade and the pre-bridge layer in order to obtain a uniform thickness. So I'll just will go back to the relevant section in the slides and that will help. Yes, so it was here. So as Professor Kapil explained in class, because of the viscous action and the adhesion of the resin to the doctor's blade in this region, say, and ahead of it also, the resin will actually adhere to the blade so that ahead there is this leading edge bulge, and at the trailing edge, well, not exactly a bulge, but the height of the column will still be far more than required. And for a triangular distribution of velocity from the part where you assume zero velocity to the blade where you assume velocity equal to blade. Okay, maybe red is not the best color to write here. For such a simple case, the calculations were performed to show that these heights are related as such. So at the lagging edge, the height of the resin column will equal twice the height of the required layer thickness. So we directly use this formula for question number 4. We assumed that the distribution of the velocity between the part of the resin between the part and the doctor's blade will be triangular, and thus the required layer height thickness will equal half of the layer height thickness at the lagging edge. That gave us the value of 20 microns. So I hope that helped. Thank you, Prakash. Thank you, Moses. Thanks for tuning in. This was week 5 of the live sessions for the fundamentals of additive manufacturing. I'll thank you for tuning in and I'll see you all again next week. Thank you.